So further pure 2 from 2022. Question number 1 is about permutations on 1, 2, 3, 4. The identity is obviously when you just don't permute. So 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. The inverse of this, so 1 is going to 3, so we're going to need 3 to go to 1. 2 goes to 4, so we're going to need 4 to go back to 2. 3 goes to 2, so we need 2 to go back to 3. And 4 goes to 1, so we need to send 1 back to 2 again. Demonstrate this is associative. Now the only thing that you can really get wrong here, this is associativity, is when you do A composed with B or B composed with C, you start with B and then go to A. It does go through this in the book quite carefully. But for example, A composed with B, you start with B and you go, okay, well 1 goes to 2, and then 2 goes to 4, so therefore 1 goes to 4. You have to do it that way around, otherwise it's not the same, right? 1 goes to 3, which then goes to 3, and you end up with a 3 here. That's wrong. So you start with B. 1 goes to 2, 2 goes to 4, and you end up with a 4. 2 goes to 4, 4 goes to 1, you have a 1 here. 3 goes to 3, 3 goes to 2, you have a 2. 4 goes to 1, 1 goes to... Sorry, I did it again, didn't I? 4 goes to 1, then 1 goes to 3, and you end up with a 3 here. Same thing for A composed with B, then C. You start with C, then compose it with this one here. So C says 1 goes to 4, and 4 then goes to 3, so this has a 3 here. Then we go to the next one, right? 2 goes to 1, 1 goes to 4, has a 4 there, and you keep going. You do the same thing for B composed with C, again start at C when you do this, and then you do the same thing for A composed with B, then C. So you start with this one here, then compose that with A there. So go from 1 to 1, then to 3, and you end up with this. These are the same, of course, and so therefore this demonstrates that it's associative with these 3 elements. It's not really a proof, I guess, but it at least demonstrates that. Explain why it's possible for this to have a subgroup order 4. Well, this is about Lagrange's theorem, so the total order of S4 is just the number of elements in it. Now, how many ways are there to permute 4 things? Well, you can send this one to 4 different places, you could send this one to then 3 different places, this one to 2 different places, this one to 1 place. That's 4 factorial possible elements, so the order is 4 factorial, which means 4 is, of course, a factor of 4 factorial. And so therefore, by Lagrange's theorem, it's possible that a subgroup of that size exists. Cool, excellent. Question number 2 then is about matrices and eigenvalues and stuff. So let's do det of m minus lambda I and set that to be 0. So take away i's from this diagonal here. Sorry, take away lambdas from that diagonal there. And okay, let's find the determinant of this. This looks like it's going to be horrific, like most of them are. But this 0 helps you out massively when you're determining the determinant matrix of this. And then the A just ends up being a minus 3A at the end here, so that's 0 as well. So that's really helpful. So all we've really got to deal with is this bit. So let's do some very careful expanding, some very careful even more expanding, some very careful collecting and grouping, and we get this, and then we can set... I did this really stupidly with all these negatives, but okay, I've got a minus here, so this equals 7, I guess, straight away. I've got a minus here, so this got to equal minus 13, I guess. I don't know why I grouped it like this, I don't know what I was on. And then all of this equals C, but I'll get to that in a second, because first I want to solve A and B. You can kind of say this is minus brackets A plus B, and A plus B is clearly 6, so that's going to be minus 6, which makes minus A be minus 8, which means, and these are positive integers, right, so you can just sit here very quickly and think of 2 and 4 maybe. 2 and 4 I think will do this, and 2 and 4 will also do this, so A is 2, B is 4 will work. You put those into this last one and to find C, and you get C as this. And then, of course, you can just put all those values into here and C into here, and we end up with those. And then using Cayley-Hamilton, now Cayley-Hamilton says a matrix is its own solution of its characteristic equation, so you can put M into here. Just replace 1 with I, because otherwise this doesn't really make sense. This has got to be a matrix as well. So put M into here, and then front multiply everything by M inverse to make this an M squared, this an M, this just 13i, and this M inverse, and then rearrange, and we get M inverse as this. You can use a calculator to work out M squared. You can use a calculator, I guess, if you want to work out 7M, and 13i is just the identity matrix of 13s. Add these together. In fact, no, sorry, don't do this, minus this, plus this, and you eventually end up with that, I think. Looks good to me, and we'll have our answer. So this frog is jumping from pad to pad here. Explain why P1 is 0. So the probability after one jump, the probability that you're on A after one jump is 0. Well, if you're on A to start with, after one jump you're either here or here. You can't not jump. So just say something to that effect. We have this recurrence relation proved by induction, this thing here, so let's just show that this works for n is 1, I guess. If we put n is 1 into here, we get this minus a half to the power 1 is just minus a half, times by 2/3 is minus a third, so that equals 0, which we've already shown. We've already explained p1 is 0, so that checks out. So let's assume it's true for n equals k, so let's be really clear, assume this thing here. And now let's consider what happens for n equals k plus 1. So go for this thing here, and replace this pk with your p with this assumption step here. So put that in there, sort this out. It's a little bit annoying, but just put the half in there first. Just notice how there's a minus here to make this a minus as well. And then what I've done is I've times this by a half, and then not times this bit by a half. I've kind of just said, oh, okay, it's a minus a half, and I'm just going to have it there. But of course that's great, because that means I can move it into here and put a k plus 1, and we get this, and I think that's of the correct form. So then we say our usual thing, and I think we're done with that thing there. I think that's good. Use the result in part B to explain why. In the long term, the probability the fog is on pad A is a third. Well, as n gets really, really big, minus a half to the power n gets really, really small, and p to the n essentially just becomes a third. So that's about that. Question number 4, so a bit of Euclidean algorithm first. So we'll start with 124. We'll just say you can use a calculator for as much of this as possible. I just tried a few things times 17 until I got really close, and I ended up with 119, so there was 5 left over. And then, of course, you can just put 17 here and do the same thing with 5s. Of course, you can do this without a calculator now. 17 is 3 times 5 plus 2. And then 2, put the 5 here, sorry, and then that's 2 times 2 plus 1. And so the GCD is 1. You can finish up if you want to, though you don't really need this line at all. And you just say the GCD is 1, so therefore they're relatively prime. Hence, solve this thing here. What we do is we start with this line here, probably, and say 1 equals 5 minus 2 times 2. And then you go to this line and you say, well, 2 is actually 17 minus 3 times 5, so let's replace that there. Expand this out to get minus 2 lots of 17, plus 6 lots of 5, plus 1 lot of 5 is plus 7 lots of 5. You can check each step in the calculator to make sure you haven't made a mistake. Replace this 5 here with 124 minus 7 lots of 17. Again, do some expanding and tidying up, and you get this. And then we can just times the whole thing by 10, because there's a 10 here, and we end up with the numbers necessary of 70 and minus 510 for our two answers. Solve this now to finish up. There's a few ways you could do this. I actually just noticed that if you times this by 4, you get a 40 here, and 40 is really helpful because 40, I believe, is 6 mod 17, because 17 doubled is 34, and then 40 is 6 above that. So if we just take, so I've times everything by 4, right? And if we just take mod of 17 both sides, because this is a multiple of 17, it just goes away. And 124 times this number here is congruent to 6 mod 17. This number here is, of course, 280, which you can then just, divide by 17 to find the remainder, and you get that it's 8 mod 17. The more normal way of doing this is to find the multiplicative inverse of 124. So you start with this here, which is what we said before this line, remember, before we times it by 10. You have this here, and then you could take mod 17 of that just to get rid of this thing here, and decide that 7 is 124's multiplicative inverse. And that's useful to know, because what it means is you could multiply both sides of this by 7, and this would just become a 1 mod 17 because of this. So we get x equals 42 mod 17. 17 goes to 34, which is 8 left over, so we're going to have 8 equals 8 mod 17. So just a couple of ways of doing that. Either one is fine. These questions you just pray for in FP2, don't you? Because you just replace the z with an x plus iy. You then group the reals and imaginaries together. You then use the idea that this is, of course, the modulus, which you could write as this. If you square both sides, you get this. So if we just square both of these, square 3 to get 9 as well, this thing here, we can get rid of the complex bit because it's just the two coefficients squared. It's just x squared plus y plus a squared. And likewise over here. We can expand everything out here, I guess. We can start collecting things together. I divided by 8, and I was just determined to use decimals because, I don't know, I was just feeling filthy, I guess. And then we can collect these three things together and say that these three things collected together must equal r squared. This is r, so we'll just have to square it. We get this. We work out what that is. We divide by this. We square root. Magically, we get plus or minus 4. Now, which is it? Well, the center of the circle is in the third quadrant, which is the quadrant where both, if you imagine the axis, it's the quadrant where both things are negative. So, well, here, if A was negative here, this would be a positive, and so would this, so therefore the centers would be negative, because you'd have x, like in... there shouldn't be x squared here, this should just be an x, apologies. But anyway, if you have the circle x plus 5 all squared, that's center minus 5, isn't it? So we want these to be positive, so therefore we'll choose A to be negative here. Find the coordinates of the center. I mean, you just put 4 into here, and you get the center immediately. 2 marks, very, very quickly. Question number 6 is solving a second order recurrence relation. So move these two things to the other side. Our auxiliary equation is now going to be m squared minus 2m plus 1 equals 0. This factorizes, and you get a repeated root at 1, which means we're going to use the form an plus b times that repeated root of 1 to the power n. Now, of course, this just goes away. This is the form that you use when it's repeated, remember. So that just goes away and you just get that bit. So that's the complementary function. We also want the particular solution, or particular whatever it's called. So we say un equals mu 2 to the power n, maybe. We'll say, well, that means un minus 1 is mu 2 to the power n minus 1, which I can say is the same as half mu 2 to the power n minus 1, because this is the same as divide by 2 there, this minus 1. Same thing for un minus 2, we can say that's a quarter. And now I can put all 3 of these results into here to get this. This cancels, and then it cancels with this as well. So we end up with mu equals 4, I believe, to make this balance out. And so our general solution is going to be this plus this with mu equals 4. And we'll have our answer. Okay, now given these two things, so u0, well, u0 according to this is just a times 0, which goes away, plus b plus 4 to the power 2 to the 0, which is just b plus 4. And then u1, according to this, is a times 1 plus b plus 4 times 2 to the power 1, which is 8. And apparently u0, which is this, is equal to 2 lots of that, so we'll set this equal to 2 lots of that, and we can, I guess, rearrange that a little bit. And now we can do the same thing with these two things. So u2, just put 2's into here, you get this. u4, put 4's into here, you get this. And then u4 is equal to 3 lots of that, so we'll put that in there, we'll rearrange this, we'll get this. And then I think if you just do this minus this, you'll get b as 28. And then if you do, then you just substitute b as 28 into there, and you get a as that, and then you can put your solution together, and you'll have the final answer. Number 7 then, it's actually, it looks like it's going to be about polynomials, but it's not, it's just a combinatorics question. P, Q, R, S belong to this set, and they can be anything that's distinct, so you've got 1, 2, 3, 4, 5 choices for P, 4 choices for Q, 3 choices for R, 2 choices for S, and that's 120. The only thing you need to be careful about this second mark is that if this is a quartic, and it is a quartic, then that means P can't be 0, because if P was 0, then it would actually be a cubic. So P we can choose between 1, 2, 3, 4, and 5 things, and then Q we can also choose between the other 5 things, because we can actually start choosing 0 again. And then we have 4 choices, then 3, and we get this thing here. A 3-digit number is this, so that's 100A plus 10B plus C, is how numbers work. N is divisible by 11 means the alternating sum of digits is divisible by 11, so I can say that's equal to 0 mod 11, maybe, is what I'll say. The sum of the digits n is even, means that A plus B plus C is equal to 0 mod 2, and then n equal to n mod 9, well, the whole number I've already said is this. Now, if you take mod 9 of this, 100 is 99, is 1 mod 9, because of 99, right? So this is just A. Again, this is just B, because 10 is 1 mod 9. And then just plus C. So you just get A plus B plus C equals 8 mod 9. So those are my first 3 things that I get from this. And it says use the first 2 properties, that's these 2 here, to show this thing here that it's actually equal to 0. Well, if it's equal to 0 mod 11, your only choices are 0, 11. You can't have 22 because you're taking away a number here. So like even if these are 9s, you're taking away and it's going to be less than 18. So we can't have that. So all we really need to decide is, can we have 11? And if these 3 things add up to 11, just add 2b to both sides. And now this thing here apparently is definitely even. But this thing over here, that's an even number. Plus 11 is an odd number. So this doesn't work. So we can't have 11, so therefore the only choice left for this here is 0. Which means that, hang on. So equal to 0 mod 11. Oh, sorry, yeah, the only choice left is 0. They have to just add up to 0. So that's it. That's what I'll say. So that's that done. And then hence determine all possible integers n. So I think I've gone about this quite a weird way, but what I decided to do was say A plus b plus c is either one of these three things. Now it can't be that thing because we've already discussed that either of those that's even. They're these things, by the way, because these are the three things that are 8 mod 9 that actually are in, like, these are three positive integers, right, less than 9 or equal to 9. So those are the only things it can be. Now if it's equal, now what I think I did was I did this plus this to get 2a, b's cancel, plus 2c equals 8 or 26, and then divide both by 2 sides by 2, you get a plus c is either 4 or 13. And then I just made a table, and I said, okay, if a is 0, which it can't be because it's a 3-digit number, so we'll start with a as 1, that makes c, 3. Now, if a was 1, c can't be 12, so we'll just ignore that. And according to this rule, if a is 1 and c is 3, b has to be 4 to make that equal to 0. So I think I get this number, and you can test all its properties, and it works. So then we'll move on to a as 2, which would make c 2 as well, and by here b would also have to be 4. You can actually just show that b has to be 4, but whatever. If a is 2, we can't make it c 11, so that would just be that. If a is 3, we can make c 1. We still can't make it 10. B is just going to be 4 again. And then if a is 4, we can make c 0, which we are allowed to do, and b is 4, and we get that. If a is 5, we can't make c minus 1, but we could try making it 8. But if we, 9. I'm still with 4, I'm still going with 4, because 4 plus 9 is 13. But the problem here is 4 plus 9 is 13. You can't take away enough b's to get to 0, so that doesn't work. And actually nothing else will work either, because you just have to take away the same non-existent b that wouldn't work. So we only have the solutions 1, 4, 3, 2, 4, 2, 3, 4, 1, and 4, 4, 0. And that will be that. Question number 8 then. If you haven't watched Eddie Wu's series of videos on this kind of complex number question, just go watch it, because it's incredible. And you, like, oh, I forgot to mention earlier actually, if you haven't seen 3 Blue 1 Brown's video on eigenvectors and eigenvalues, go watch that too. But yeah, Eddie Wu has a series of videos about this. It's incredible. Essentially what this draws, firstly write it like this obviously, because then you can actually get the points out. So a plus 5i and 2 plus 5i probably look a bit like this. And now if this angle here is less than pi over 2, you make a major arc, and if it's positive it's above the thing. So you make a major arc like this of a circle, whereby, like, if you imagine a line coming out to there and then to there, this angle here is pi over 3 that you'd create. So that's that. Again, Eddie Wu has a fantastic video talking about that in detail. Explain why the center of this circle here, if we imagine this as a whole circle, has center coordinate 5. Well, that has x coordinate 2, and that's 8, so we just take the average and we get 5. Determine the radius of C. So we've got a center here. We can say this distance across is 6 from 2 to 8, and then we have a radius in here. And now thinking about what I just said, if we draw a line coming out to the arc of this circle and then to there, that angle you'd form is pi over 3. Well, by GCSE circle theorems, that means this angle in the center, double the angle on the circumference. This angle is 2 pi over 3. And then we can just, if this is r of course, and this is r as well, we can just do some cosine rule, and we can say 6 squared equals r squared plus r squared minus 2r squared times cos of this. You put that in the calculator, you get r as this. So that's the radius, and then determine the y-coordinate. So I just drew a little triangle coming down from here. This distance is 3 because it's halfway along. That's r, which is 2 root 3. I think I can work out this length by Pythagoras by doing that. And then of course this is already 5i high, these points. So we're just going to do 5 plus root 3, and that will be the distance up to the center of the circle. Excellent, yeah, Eddie Wu's video, go watch it. So for this kind of reduction formula question, always break up the thing that you've been given. Now there are two things worth trying here, either n minus 2 with a 2 there, or n minus 1 with a 1. Obviously I'm just doing the thing that works, but always think about trying both at least. Now this works quite well because you can try doing integrals by parts. We can integrate, I mean, in case I do integrals by parts differently, I think. I just pick one of these two things that I want to integrate, and I integrate it a couple of times, so that's there. I'll then leave the other one alone the first time, minus the integral of, and then I'll differentiate this one and put it over there. So that's n minus 1 over down there, make it into n minus 2. There's also a 2, and then there's also, obviously, the derivative of sine 2x is 2 cos 2x. So we get this, and yeah, then this is quite nice because the sine makes both of these things go away, so this all just ends up being 0. And then this minus can cancel out with that minus. The 2 cos squares, the 2's can also cancel with the 2.5. The cos and 2x and cos 2x become cos squared, which you can then write as 1 minus sine squared. And then you can expand this out to get this. You can also factorize out the n minus 1 since it's not doing anything with the integral. And then you can, of course, break this integral into two pieces, because you're allowed to do that, of course. And this is just in minus 2, and this is just in. So I think we have in equals n minus 1 into in minus 2 minus in. So that's my line here. You can expand this out if you want to. You can then add this stuff to both sides. You just end up with n ins, divide by n, and we have what they wanted us to get. Hence determine this. So we've got sine to the 5, cos to the 5, so we should be thinking maybe about using that. We can write this with all to the power 5, can't we? And now just be careful, 2 to the power 5 is 32, so I need one extra 2 outside, not being raised up to a power, to make it 64. But here, of course, this is just sine 2x. That's the formula that we all know and love. So, of course, this here is just sine to the 5 2x, so this entire thing here is just going to be of this form with n equals 5. And don't know why I wrote that again. And this, therefore, is just going to be 2 lots of I to the 5, or the fifth I, which we can use this formula for. It's 5 minus 1 over 5, and then I3. And I3, of course, is just this integral with a 3 put here. But this here is just, again, using this formula here, is just 3 minus 1 over 3 I1, because you would reduce that by 2 again, and I1 is just the integral of sine 2x. So that's quite cool. I've simplified a little bit of this. I can integrate sine 2x to minus a half cos 2x. I can put my two limits in, I can multiply some fractions out, and I eventually end up with that. Question number 10 is the last question on here. It's about surface integrals. So apologies for it's slightly blurry, that's annoying. But anyway, I think it's readable. We're going to get out the formula book, obviously, and find this. Now, the only thing we have to be careful of here is this is an integral around the x-axis to find a surface. We're integrating around the y-axis. So all we have to do is change that y for an x. And we could change these y's and x's over, but it's symmetrical under the root, so we don't really need to. So we just have to replace this y with an x. So we find dx by dt and dy by dt as normal. We put those in, and that just needs to be an x, which is this thing here. And this will be what we have to try and deal with, integrating between 0 and 1, of course, because of this. I'm actually just going to write this back as x, because I want to save some space, and I want to deal with this first. So I factored out a 15 squared from here, and this is just 900. And then I can factor out a 225, which roots to a 15, and then 15 times 2 is 30. And then that just leaves 4 here, because 4 times 225 is 90. And then we can finally expand this out. We can collect together some things, and things go really well here, because this just factorizes to t squared plus 1, I believe, all squared. We cancel the root and the square, which we're sort of allowed to do, and now we can finally replace this x back with here, because I'm ready to get a bit more space and write some more things down. So now I can expand all this out. I first actually factorized out of 5, which is cool. Then I expanded everything out, and then collect everything together, and you actually end up with the thing that they wanted you to get. Good, and now all it's asking us to do is find the total surface area of the plant pot, which just means figuring out this integral here. So we integrate this. It's no marks for doing this, because it's really easy, I guess. And we get this, which turns out into this. Now that's not the answer, because notice how it's very careful to say it has a flat circular base of radius 10, which means the curve only starts 10 centimeters along. That's when the curve starts. So when you integrate this curve around, you actually miss the distance along 10 and 10 either side, which, of course, going back to this picture, is just a circle, radius 10. So we just need to add on pi times 10 squared. We just need to add on this base circle, which you don't get from this integral, because this integral is just 0 at 10 along. So we add in this in, we get 775 pi, and that will actually be our answer here. And then it says each plant pot is covered with uncoated plate, both inside and outside. So let's work that out as a decimal and times it by 2, because we're painting inside and outside. We get this, which is centimeters cubed, because everything was in centimeters. Now this here, there's 100 centimeters a meter. Square it, you get 100, or 10,000, so 2 zeros become 4 zeros. Times it by 12, and you get 12. No, you don't. You get, this is what, 10,000, so you get 120,000 centimeters squared. And so that's how much each tin can cover. So divide that by how much you need for each pot, and you end up with 24.6. So I'm going to round and say you can do 24 pots fully. Just round down. Give a reason why this might not be accurate. thickness of the thing counts, maybe the surface is not smooth, maybe something like that, or you can just say the curve just doesn't accurately reflect the edge of the plant pot, and that will do too, and that will be the entire paper done. Thanks for watching.